Hi everybody, welcome back to the channel. So in this video, we're going to start looking at reactions involving benzenes, which in my opinion are the most fun reactions in OChem. The only thing I will warn you about is keeping the reactions organized, because if you don't, it becomes really easy to start doing reactions that benzenes cannot do, and we don't want that. So hopefully this series of videos will help you keep everything organized and make learning benzenes really fun. So again, it's all about keeping organized. So what I'm showing you here is I guess a flowchart that I made that hopefully will help you keep track of all the reactions that benzenes are involved in. And just to let you know, the flowchart I'm showing you right now, it's not complete, but we will complete it over the course of the next few videos. Now, the focus of today's videos are on the reactions coming directly off the benzene. And these reactions fall under a category called electrophilic aromatic substitution reactions, or shortened as EAS reactions. And in these types of reactions, we're going to substitute a hydrogen on the benzene for an electrophile. So just to reiterate, those arrows coming directly off the benzene are representing EAS reactions. And again, in these types of reactions, we're going to substitute a benzene hydrogen with an electrophile. Now, there's 4 EAS reactions you're going to encounter, but thankfully, they all have a very similar mechanism, which means less work for you. And basically how it works is that we are going to first generate an electrophile, and this is what takes up the majority of the mechanism, and it's what is different across the 4 EAS reactions. But once we've generated the electrophile, benzene with its electron-rich double bonds is going to attack the electrophile and add it to itself in place of a hydrogen. So again, once you've made the electrophile, benzene's electron-rich double bond will act like a nucleophile and attack the electrophile. Now, the electrophile will end up on one of the carbons that was in that double bond, and the other carbon in that double bond will be left with a positive charge. And there's a couple of resonance forms that can come out of this, so let's be sure to include that here. Now, the hydrogen on the carbon that has both the electrophile and the hydrogen attached to it will become acidic. Why? Because benzene wants to be aromatic again. Being aromatic means you are stable, and being stable means you are a very low energy, and the universe just loves low energy products. So benzene just wants to be loved again by the universe, so it's going to tell hydrogen to get out of here, to get lost. And hydrogen is sad and leaves with a base that is floating around in the solution. And it gives its electrons back to benzene to remake the double bond, and voila! We have restored aromaticity. Benzene and the universe are now happy. It sucks for that hydrogen though, but this is what we're going to see across all the EAS mechanisms. So the first EAS reaction we're going to look at is halogenation of benzene. So we're going to substitute a benzene hydrogen for a halogen. Now before we take a look at the mechanism, let's understand the role of each reagent needed for this reaction to occur. So first, you need a halogen source, so that could either be Br2 or Cl2. The next thing you'll need is a catalyst. So that could either be FeX3 or AlX3, aluminum trihalide, where again, the X could be bromine or chlorine. Now, there has to be a catalyst. This catalyst is essential. Without the catalyst, there would be no reaction. And it's really important that you understand that heat and light are not catalysts. It has to be FeX3 or AlX3. And the reason why it's so important is because it's going to help us generate the electrophile. And this will all make sense once we take a look at the mechanism, but this catalyst is essential. And the last thing we're going to need is a nonpolar solvent to get the product you see at the right-hand side. And a very common nonpolar solvent is CCl4. So now let's take a look at the mechanism. So as I said before, the first thing that is going to happen is the generation of the electrophile. So take a look at FeBr3. As you know, bromine is much more electronegative than iron. So this difference in electronegativity means that the bromines will pull the electrons in iron towards themselves, causing partial negative charges on the bromines and a partial positive charge on the iron to form. Now in the solution, we have Br2 floating around, and as we know, Br2 is nonpolar. But if you recall from Gen Chem, what are known as instantaneous dipoles can be formed. So imagine you have a bottle of water and all of a sudden you jolt it. For a second, all the water goes to one side of the bottle. The same thing essentially happens with Br2 in solution. At some point, it's going to be jolted, and all the electrons are going to end up on one side of the Br2 molecule, producing a very, very temporary partial positive charge on one of the bromines and a partial negative charge on the other bromine. You know, opposites attract, so this temporary partial negatively charged bromine is going to be attracted to the partially positively charged iron, and bam, we get the product on the right-hand side. So now, bromine attached to the iron has a positive charge. It's sad. Bromine is an electronegative atom, meaning that it likes negative charges, but right now it has a positive charge. So what's going to happen is that the positively charged bromine bonded to the iron is going to start tugging on the electrons in the bromine it's attached to. It's basically saying, hey, no fair, share some of your electrons with me. So that bromine, tired of hearing all this nagging, is going to give a little bit of its electron density to its neighbor, and we get this very, very slight partial positive charge on the outermost bromine and a very partial negatively charged on the innermost bromine. And what's going to happen is the electron-rich double bond in benzene is going to take advantage of this very slight partial positive charge, and everything's about to look very familiar to you. So we have established our electrophile, and an electron-rich double bond in benzene will attack. This results in a loss of aromaticity, as I mentioned, and being aromatic means the world to benzene because the universe just loves stable things. So benzene's going to tell the hydrogen on the carbon with the electrophile on it, hey, you got to go. And that hydrogen's going to say, fine, and just packs its bags and leaves with the extra bromine attached to the iron. And as hydrogen leaves, it drops its electrons, and voila, we have our aromatic benzene restored. We have our catalyst regenerated, and now we have a benzene with a halogen on it. So we just saw how we can add a halogen to a benzene using a halogen source, right? Either Br2 or Cl2, a catalyst, right? We saw how the catalyst generated that electrophile, and a nonpolar solvent like CCl4. So now we're going to look at how we can add an NO2 group to a benzene. So to substitute a benzene hydrogen with an NO2 group, we will need to use concentrated nitric acid along with sulfuric acid. Now the nitric acid is what is going to give us our NO2 group, and the sulfuric acid is going to help us in getting that NO2 group. And we're about to see that in the mechanism. So on the left side, we have nitric acid and sulfuric acid. So it's really important for you to know that sulfuric acid is actually much more acidic than nitric acid. And so what's going to happen is that the nitric acid is going to act as a base. And specifically, it's going to be the oxygen attached to the hydrogen in nitric acid that is going to be the basic oxygen. So this oxygen is going to remove a proton from sulfuric acid, generating the products on the right-hand side. So now you may be wondering, wait, why did it have to be that oxygen that removes the proton? And the reason is resonance. If any of the other oxygens in nitric acid had taken the proton, we would lose the resonance happening between these two oxygens. And remember, resonance is a stabilizing mechanism. And we just talked about how the universe loves stable things, so this is the reason why that oxygen must be the attacker. So now, looking at the products just produced on the right-hand side, we see the conjugate base of sulfuric acid, and we also see protonated nitric acid. Now notice that the oxygen that was just protonated in nitric acid looks a lot like water. And what do we know about water? Water is a good leaving group. Now also notice that the nitrogen next to the positively charged oxygen is also positively charged. And what do we know about charges? Like charges repel. So we have a good leaving group, water, and we have repulsive forces, right? The two positive charges next to each other. And this is going to cause water to get kicked off of the nitrogen, and it's going to result in the production of the products on the right-hand side. Now this NO2 group just produced is going to serve as our electrophile. The nitrogen has a full positive charge, indicating that it's electron deficient. So, as we've seen before, the electron-rich double bond in benzene is going to attack the electrophile. This will result in benzene losing its aromaticity. But benzene wants to be aromatic again. Remember, benzene wants to be loved by the universe, and the universe likes stable things. So, benzene is going to tell the hydrogen on the carbon with the electrophile on it to get lost. And so that hydrogen says, okay, fine, and asks a base in solution to take it away. The conjugate base of sulfuric acid, right, HSO4-, is a reasonable base in solution that can take the hydrogen away. As hydrogen leaves, it dumps its electrons with benzene, and voila, we have restored aromaticity. So far we've looked at how we can halogenate a benzene and how we can add a nitro group to a benzene. And now we're going to look at how we can add a sulfur group to a benzene. So to substitute a benzene hydrogen with a sulfur group, all you have to do is add sulfuric acid. Now something I like to point out are these reversible arrows. So for all the other EAS reactions I discussed so far, none of them had reversible arrows. So it's important for you to know that sulfonation, or just adding sulfur group to a benzene, is the only EAS reaction that is reversible. So when we add the halogen or the nitro group to benzene, that's permanently added. They can't be removed once they are added. However, that's not the case with the sulfur group. We can remove the sulfur group by applying some heat. So now let's take a look at the mechanism. Now acid-base reactions are constantly occurring. So it's reasonable that protons will be exchanged between sulfuric acid molecules. When a sulfuric acid molecule gets protonated, we get this H2O plus group. And what does that resemble? Water. And what is water? A good leaving group, right? So water is going to end up leaving, and we get the products in the line below. Now when water leaves from the sulfuric acid, it leaves a positive charge on the sulfur atom, but that positive charge is being stabilized by resonance with the oxygen. Now remember how we said bromine doesn't like positive charges? Well, neither does oxygen, and that's because oxygen is electronegative and likes negative charges. As a result of this, oxygen is really going to tug on the electrons in hydrogen, and hydrogen is going to be like, I'm out, and signals for a base to come and take it away from that oxygen. So, the conjugate base of sulfuric acid is a reasonable base that can accomplish this. So this generates the product seen in the line below. Now sulfur is bonded to 3 oxygens. Now remember that oxygen is more electronegative than sulfur. So because of this electronegativity difference, we're going to have electrons being pulled toward the oxygens, generating partial negative charges on the oxygens and a partial positive charge on sulfur. So now we have our electrophile. And this is going to seem very familiar now. So the electron-rich double bond in benzene is going to attack the sulfur, and we are going to lose aromaticity. But benzene wants to be loved by the universe again, so it tells the hydrogen on the carbon bonded to the electrophile to get lost. And hydrogen's like, okay, fine, but of course with a little sass, and signals for a base to come and take it. Now here's something really interesting. So my professor hypothesizes that it's the sulfur group itself on the benzene that takes this proton off. And the reason she believes this is because intramolecular reactions tend to occur much faster than intermolecular reactions. In other words, do you think it makes more sense that another HSO4 minus comes in, and then it takes the proton off, and then it has to come back to protonate the sulfur group on the probably not, right? So she believes that it's the oxygen in the sulfur group that's going to snatch the proton. And when it snatches the proton, right, the hydrogen is going to dump its electrons back on the benzene, and voila, we have restored aromaticity. So we've seen how we can halogenate a benzene, how we can add a nitro group to the benzene, and how we can add a sulfur group to the benzene. And in the next video, we're going to continue building this tree and see what other reactions benzenes are involved in. And that's it for this video. Great job, and you've got this.